the RSNA. This is the Radiology Artificial Intelligence Podcast. My name is Paul Gee, and I'm a radiologist at the University of Maryland and co-host of the podcast.
And my name is Tejani, and I'm a radiology resident at the University of Texas Southwestern Medical Center and co-host of the podcast. Each month, we dive into the hottest topics in radiology AI and talk with leading experts, thought leaders, and movers and shakers in the field.
Welcome to this episode of the Radiology AI podcast. You may have seen our recent publications detailing breast imaging datasets. Today, we catch up with Drs. Trivedi and MinJae to learn more about their experience organizing the EmBED breast imaging dataset, also known as EmBED, as well as their thoughts on best practice recommendations for those looking forward to exploring the EmBED dataset.
Dr. Trivedi is an assistant professor in the Department of Radiology and Imaging Sciences with a joint appointment in the Department of Biomedical Informatics at Emory University School of Medicine. Dr. Trivedi is also the co-director of the Health Innovation and Translational Informatics Lab at Emory University, where he works on multiple machine learning projects related to radiology and development of large data sets. His clinical expertise is in emergency and trauma imaging with fellowship training in musculoskeletal imaging. Dr. MinJae is currently an assistant professor of data science in the School of Data Science and Analytics at Kennesaw State University in Georgia. His research interests lie in the area of healthcare data science, with a focus on its application in medical imaging, clinical text, and clinically oriented speech. He spent the early years of his career developing a variety of clinical decision support tools to assist combat medics on the battlefield. His ongoing projects aim to develop various early cancer screening platforms that are fair and explainable for the detection of breast cancer, oral cancer, lung cancer, and hepatic metastases. So Hari and MinJae, thank you both for joining us for the Radiology AI podcast. Paul and I are so excited to have you, and congratulations on the EmBED dataset. This is probably the first breast imaging dataset containing annotated screening and diagnostic mammograms. Can you tell us more about the dataset? Hari, if you don't mind, we can start with you. Just tell us, what is it composed of? And let's start there.
Yeah, absolutely. So we did a retrospective extraction of all mammograms from our university from 2013 to 2020. That's about how far back we could do digital pulls. Ended up being around 110,000 patients and roughly 400,000 exams. And sometime in 2016, 2017, we started doing combination acquired 2D and 3D mammograms. So there'd be digital breast tomosynthesis plus 2D mammograms acquired in the same acquisition, which makes this kind of a unique data set because some places that switch to DBT only do DBT plus synthetic 2D, or sometimes called CView, which is a trade name. But we actually have full FFDM, full field digital mammograms, and digital breast tomosynthesis images. And then a couple of other things that are unique about the data set are that our patient population at our institution is split pretty evenly between African American and white patients. So we've got about in the data set about 45% African American and 45% white patients and 10% other, which as far as I know is the first data set of its kind in medical imaging with this type of distribution. And it's especially important in breast imaging because it's known that Black patients have a different risk profile for breast cancer compared to white patients. And then the last thing I think that makes this data set unique is the annotations. So we have ground truth pathologic outcomes for patients, not just by cancer, no cancer, but we have their specific diagnoses, what type of cancer, what subtype, if they had a high-risk lesion, if they had a borderline lesion, we've got that information. And we've also got around 40,000 lesion annotations with regions of interest annotated directly on the screening mammograms, which were done by the original interpreting radiologist to show where the lesions are. So what we can do is we can take a cancer, move backwards to the screening mammogram, find out the imaging characteristics that the radiologist used to describe that lesion, whether it was a mass, calcification, asymmetry, and then actually localize that lesion on the mammogram.
That's wonderful. That sounds like an immense amount of work, by the way. I mean, walk us through how this is curated. Where did it start? And, if we could step one step back too, what was the inspiration?
When I started as a fourth-year resident and fellow, that was 2015, 2016 timeframe, right when artificial intelligence was becoming the hot topic, not just in radiology, but everywhere. And a lot of people at my institution were looking for applications to radiology. And mammography kind of jumped out as one of the first potential large scale applications for AI in radiology because of a few reasons. One is the sheer volume of mammograms that are done annually. So in the US, either beginning at age 40 or age 50, depending on the guidelines you follow, every woman should be receiving a screening mammogram, or almost every woman should be receiving a screening mammogram. So that volume is huge. It's greater than 40 million exams per year. So that's the first thing. The second thing is this is becoming less true now, but is still true to some extent, that creating high quality machine learning algorithms requires structured data. And the better input data and the better homogeneity of that input data you have, the more likelihood you have of creating a model that works pretty well. And it just so happens that breast cancer screening is heavily kind of dictated by the BI-RADS manual, the ACR BI-RADS manual, which not only affects management or dictates management of patients, but also dictates how those findings should be described. So if you have a mass, you have to describe the shape of the mass, the margins of the mass, the density of the mass, and there's these very finite list of descriptors that you can use for masses, calcifications, asymmetries. And then the last thing is the management for breast cancer or high risk lesions or borderline lesions is pretty well defined across the United States. There are obviously gray areas, but all of those things combined lends itself well to having the pieces to make a very large scale, very homogeneous data set that would hopefully generalize well across different institutions. One thing I neglected to mention is that the acquisitions for the images are also heavily regulated. So patient positioning, how much of the chest wall must be in the image, the nipple must be in profile, all of those things. So the images are homogeneous, the imaging characteristics that are used to describe are homogeneous, the list of outcomes or findings or pathology diagnoses is finite. The scale is huge, right? So I began with this project when I was a trainee. And then when I started at my current institution, it just made the most sense to take what I'd learned previously and apply it here. And so, we kind of ran with it. It's been a 3-year process with lots and lots of people helping along the way. But, we're very happy to get it to a point where we can ship it out. It's continually being modified and reviewed. But, we're very happy that this resource is now available.
Paul, I don't know about you, but the more I hear about this, the more questions I have. And it's just so exciting that this is available as a public tool. And we can definitely get back to that more in just a bit. But going to the more technical aspect, and MinJae, maybe we can ask you this question, but there was some AI involved. There was natural language processing in this design in terms of annotating the reports. Is that accurate? And maybe you can tell us more about how you incorporated the RAD path association and labeling.
So we did use some of those tools, but in the context of creating dataset. So we could have done something further than just creating the dataset, but our philosophy, as far as I know, is just leave it up to the users. So we mainly utilize those tools to identify weird cases or potentially wrong curations, or if something weird happened with the dataset, then for the best integrity of dataset, we used to flag some kind of red flag. So in that context, we used those tools, but we did not really use it further to touch the actual information contained in the dataset.
Yeah, so I can put a little bit of color on that. So we're very fortunate that at our institution and many other institutions, there's a piece of software used that standardizes the reporting workflow. And so the radiologist pulls up a screening mammogram or a diagnostic mammogram and then clicks a series of boxes for breast density, for findings, for BI-RADS score, and for overall plan for that patient. And that is all of that text information is saved in a tabular format and then exported into what appears to be a free text report, but is actually structured text based on what the user or the radiologist clicked during the original interpretation of the exam. So we're able to extract the vast majority of that tabular data is already in tabular form, but it is subject to human error. So what we ran into along the way is sometimes, for example, for listeners that have familiarity with breast cancer screening, you would have a diagnostic exam with a BI-RADS 0, which should never happen, right? BI-RADS 0 should only be applied to screening exams in the vast majority of cases. And so we pulled the radiology reports and the pathology reports for these cases so that we could troubleshoot. One of the things that we wanted to check actually was pathologic outcomes. So the pathologic outcomes, and I think this is what you're referring to, Ali, when we talk about the NLP models, we did train and build a separate NLP model for extracting ground truth pathologic outcomes from radiology reports. And the reason we did this is that our original pathology outcomes were generated from the tabular data, like I mentioned. Now, that data is input by an administrator, nurse practitioner, PA in the Department of Breast Imaging or the Division of Breast Imaging. And it's subject to human error. So what they do is they take patient is flagged to having had a biopsy or a lumpectomy or mastectomy, and it's put in a queue to follow up and then add that data back into our software to track what was the final outcome for a lesion. And all of that information is coded manually. There's over 200 pathologic outcomes that this administrator can code into the database. So a couple things might happen. One is they may miss the fact that this patient had a pathology specimen, and that information may never get coded into the database. The second thing is that data could be coded either incompletely or incorrectly. So they could have missed one of the diagnoses or typed in the wrong code and gotten the wrong diagnosis in there. And so for that reason, we actually built our own annotation tool to allow us, we have 5 users annotate about 5,000 or 6,000 pathology reports, and then trained a separate hierarchical model that would go down the pathway and then determine if was this an invasive cancer, non-invasive cancer, and then extract the actual diagnosis. And that's from the free text report. And then using that, we could compare the data that was encoded in our structured database with the model predictions from the NLP model and use that as an error checking mechanism to look for any mistakes. The second reason to do that is, as large as this data set is, it's still only a single institutional data set, right? And so if we want this data set to grow beyond our walls and not be restricted to sites that use the same software that we use, we needed a generalizable NLP model that could take a pathology report and extract pathologic diagnoses from this. And so this paper is currently in review, but we did just that. We had 2 external validation sets, one from Mayo and one from Mass General, and tested the model on their data. So totally different. And pathology reports are truly free text. So they're written by different pathologists, different style, different lexicon, sometimes different lexicon depending on what those pathologists prefer. And as you might imagine, we did observe a drop in performance for individual diagnoses, but as far as determining whether it was invasive cancer, non-invasive cancer, high-risk lesion, the performance was in the high 90s. So what that means is that somebody else at another institution could use this tool to curate their own data set and build something similar.
That's wonderful. And is that tool available?
Yeah,
the separate NLP tool?
It's actually posted up on Hugging Face. So when we submitted the paper, we posted it on Hugging Face. We can drop a link later, but you can paste in any breast pathology report and it should return to you the hierarchical results of what class. We have 6 classes: invasive cancer, non-invasive, high-risk lesion, borderline lesion, etc. And then within each of those classes, you may have anywhere from 5 to 15 individual diagnoses. So I would say it covers approximately 95 to 98% of potential diagnoses in a breast pathology report. If we want to be completely exhaustive at 100%, that list would grow to over 200 or 300 diagnoses. So we stuck with, the 60 some odd diagnoses that were most frequent.
That's wonderful. And let's talk more about the QC process. Was there any formal method for quality control? And we can talk more about the actual images. I know, Hari, you mentioned there's so many factors to consider, right? Laterality, making sure that the image quality is appropriate in terms of the markers that we look at for breast imaging, in terms of having the nipple in profile and those other considerations. So talk us through what you instituted as a QC process.
Yeah, absolutely. I think MinJae probably can start with that because MinJae did a lot of work around extracting tissue from inside paddles for special views and things like that, which is not strictly in the QC arena, but is a very important part of the pipeline, right? Identifying those images first and then extracting the tissue. So maybe MinJae, you want to.
Yeah, I think what we did, there are two different pathway that we took. First is the QC control based on some of the known problems that, for example, extracting the tissues inside the paddle, or there can be some mismatch that can happen by human mistake, and those are well known. Then we definitely work on those individual issues and implement whatever tool we needed to implement. There are also another QC control, which is another large. The other side of ARM is case by case guided. So while we work on actual model development, or sometimes descriptive analytics, see what's in the data set, or sometimes we just pull out some of the examples randomly, we sometimes run into some weird cases that we could not explain, and that guides our another QC process that we investigate what happened. We sometimes go back to PAC system and then track down the individual patients with those concerns, and then implement tool if necessary.
Yeah, I think this brings up just a really important general point on QC for large data sets, whether they be mammography or any imaging or even non-imaging, is that you actually don't know what kind of mess you're going to have inside the data set, for lack of a better word, but you don't know what disaster you're going to encounter until you encounter it. And I would say 90% of the issues we found with the data set occurred when somebody started building a cohort of patients. Oh, let me find all the patients with invasive cancer. Let me find all the patients with, age over 50 and any set of parameters. And you start digging into that, and either the number returned is too big or too small, or you start looking at the images and they're not what you expected. And then so it's kind of, you then backtrack as far back as you can go to identify the issue, usually write some kind of script code or helper model to correct that issue. And then you propagate that fix back to the entire data set. And then you try again. And that's a process that each time we do that, we make a note. So that task now is added to the QC process for future data pulls, meaning this data set will be updated every 6 months. And we have a list of 20 or 25 items to QC that were discovered during the original creation of this version one of the data set. And that's kind of what, and this same thing is happening in another data set we're building for knee radiographs. You actually don't know what challenges you're going to encounter until you encounter them. And I'm confident that we have not discovered all of the potential issues inside of this data set. We won't know until somebody comes to us and says, hey, I was trying to build a data set for a cohort for XYZ, and this is not adding up.
Yeah, so I think that's all really interesting and really important for anyone who's considering building a data set. I think the lessons you guys have learned are going to be incredibly helpful for our listeners and researchers all over. But you've gone through all this process, and at this point, the data set seems like it's in pretty good shape. I'm curious, beyond just the development side, what were some of the use cases that you had in mind when creating the data set?
So this data set has so much detail, and that it kind of opens up the opportunity for various research. But what interested me the most was the fairness in AI, in specifically in breast cancer imaging. So this data set, probably the only data set publicly open at the same time, has some demographic information. And with that, we could implement models, preferably state-of-the-art models, but at the same time, we can go back to our development process and implementation to see if there's any particular group of people disadvantaged by the model. So that is one large piece that we are working on, and also the granularity of the data set opens up opportunity. You can design your experiment with the even better internal validity. You can specifically define your population of your interest and then perform experiment. And the last thing is the quality of pixel image itself. So those images are taken in contemporary clinical settings, meaning that you have a better quality. And better quality means better model that can be applied and implemented in clinical environment.
Yeah, that's all super exciting. Can you tell us about the availability of the data set? I know that you published this really awesome paper in Radiology AI, and I think it's hosted up on AWS, but what's the current status of it?
Yeah, absolutely. We partnered with the AWS Open Data Program, who've been fantastic, by the way, to host the data set. It's about 1.5 terabytes worth of data. The portion that we hosted was 20% of the full data set. So all of the metadata, all of the pathologic outcomes, and all of the imaging for 20% of the patients. That comes out to roughly 70 to 80,000 exams, 700,000 800,000 images, and is a combination of tomosynthesis, C-view, and 2D images. We are having some issues with the tomosynthesis images because they're locked in this proprietary format. We actually have to get some software to unlock them. But besides that, it's available. Anybody can request to download the dataset. So we have had this dataset now requested and provided to, I think we're on 52 institutions globally. It was really interesting to me to see the distribution. Only about a quarter of those or less, maybe even 20%, are in the United States, and the other 80% are international from everywhere, which has been pretty cool. And if people would like access to the remainder of the data set, then we have a mechanism where we can provision accounts inside of our own environment. And we have researchers from 3 or 4 institutions joining the weekly meeting, getting more hands on with the data, and they can have access to the full data set. So those are kind of the two options. Some people just want to download and play with it on their own, which they can do. And if they want to come, or let's say somebody just doesn't have CPU, GPU, but they want to play with the data, then we've got pretty powerful server they can come in on and use. And this is all supported by the AWS Open Data Program. They support all ingress and egress costs and allow us to share this.
Wow, that's pretty incredible. So it seems like this data set's already having a tremendous reach and influence both here in the US and probably more so outside of the US. Thanks for joining us for this episode. We hope you enjoyed the conversation.
Check out the second part of this conversation in the next episode of the Radiology AI podcast. Thanks to all of our panelists involved in the conversation and for their fantastic work on the EmBED.
We hope that you've enjoyed this episode of the Radiology Artificial Intelligence podcast. Shout out to Uriah Shemchisen for our podcast music and to the RSNA podcast staff.
Email us at podcasts@rsna.org anytime with questions, feedback, or suggestions.